There are three categories of web guiding systems: unwind, rewind, and intermediate. However, due to limitations of time, this presentation will deal only with intermediate guides. And in that category, there are two subcategories. There are steering guides like the one illustrated here, and there are displacement guides in which the guide roller and the entry roller pivot in tandem. They are mounted in a rigid frame which pivots about an axis in the pre-entry span. There are four key components in every system. There is a guide roller which shifts laterally and pivots at the same time. There is an actuator which drives the guide roller. It may be a motor-driven screw or a hydraulic or pneumatic cylinder. There is a sensor which detects lateral deviation of the web edge or of a printed registration mark. It may use light, ultrasound, or airflow. And there is a controller which amplifies deviation of the sensor signal from a set point and amplifies it to drive the actuator in a direction that reduces error. Here we have the block diagram of a system like the one on the previous slide. These are proportional systems in which control actions are continuously updated. The analysis of systems like this involves some challenging mathematics which you'll be pleased to know we won't get into today. We'll do that by using animated simulations to illustrate behavior, and the focus is going to be on the web portions. There is a closed loop indicated by the circular arrow which tries to keep the web position continuously on target. The blocks, framed in red, involve web dynamics. Two are inside the control loop, so results are going to depend as much on web behavior as vendor-supplied components. Results also depend strongly on web behavior outside the control loop. There are delays in all of these blocks, and delays cause problems for control systems. Sensors and controllers are rarely an issue, but actuators unavoidably contribute a significant delay. For example, converting the rotational velocity of a motor to lateral position takes time. Control engineers call this integration delay. By itself, integration delay in the actuator doesn't prevent high-performance control, but it doesn't leave much room for delays caused by the web. Webs move with rollers, but they also move on them. When a web approaches a roller at any angle other than perpendicular to the roller axis, it will track laterally in a direction that takes it back to a perpendicular condition, which we call normal entry. Normal is just another word for perpendicular. And the lateral speed of the motion will be equal to the product of the surface speed of the roller and the entry angle. And in this diagram, the entry angle is the net difference between the roller angle theta sub r and the web angle theta sub w. The angle of entry is complicated by the fact that a web doesn't behave like a perfectly flexible string. When it's shifted laterally at either end, it bends in its own plane. The dashed lines in this diagram represent a web after it's settled down following a shift in a guide roller. The shape is like that of a cantilevered beam anchored at the upstream end, but modified by web tension. All of the bending will be near the upstream end. And from the perspective of the guide roller, it appears to pivot about an upstream point called the bending center. The distance of the bending center from the guide roller is K sub c times L, where K sub c is a coefficient called the curvature factor. K sub c ranges from 2/3 to 1, and it's a function of web material parameters and span dimensions. For typical applications, it'll be closer to 2/3. High tension or low bending stiffness will cause it to increase towards 1. Notice also the center of rotation of the guide roller, which is called the instance center. Its location relative to the bending center has a big effect on performance of the system. When the web's not in a steady state, for example immediately following a change in upstream position, the downstream end won't be normal to the roller axis, and the shape can become much more complicated than shown here. Now we're going to talk a little bit about the entering span dynamics block. It has two inputs. One at the downstream end is from the guide roller position, and the other at the upstream end is from disturbances in lateral position that come from upstream sources. We'll start with response to the guide roller position. These are time plots which illustrate three possible situations. There are two curves in each plot. The yellow one is the lateral position of the guide roller, which is basically a step change. The blue curve is the lateral position of the web at the exit of the guide roller, which includes the tracking motion on the roller surface. Imagine that the guide roller is manually jogged a centimeter while the web's running and the control system's turned off. If the instant center distance is less than the bending center distance, the web's going to be oversteered, meaning that the change in roller angle which accompanies the lateral motion of the roller will be too great, and the web will have to track forward from its initial position to achieve normal entry. If the instant center is greater than the bending center distance, the web will be understeered, meaning that the change in roller angle will be too small and the web will have to track backward from its initial lateral position to achieve normal entry. The optimum situation for a guiding system is when the instant center and the bending center coincide, and this is known as neutral steering. I should mention that in the paper that accompanies this presentation, the words backward and forward have been swapped. You need to correct that in that paragraph. Now let's look at the response of the entry span to a step change in lateral position at the entry roller. In the graph on the left, the yellow curve is the input disturbance at the entry, a 1 centimeter step change in lateral position. The blue curve is the resulting output, lateral position at the guide roller. And the graph on the right is a plot of lateral position along the length of the span, 28/100ths of a second after the change began. Now, the next slide features an animated version of this second graph over a full 2.5 seconds. The vertical axis will be lateral position of the web, and the horizontal axis will be the position along the web. Here you see the step change very quickly on the left, the input, and then a little more slowly the output change at the guide roller, which occurs due to the normal entry effect. The exit span is the natural location for the guide sensor, because that's where the full effect of the guide roller is first seen. Now, if the guide roller pivots in the plane of the entry span and has 90 degrees of wrap, the exit span will behave as though it's running between a pair of parallel rollers. And that's exactly the situation that we illustrated in the previous animation. Now, when the sensor's close to the guide roller, it sees the immediate effect of the roller's lateral motion. However, when it's located close to the exit roller, most of the motion it sees is from the relatively slow tracking caused by the normal entry effect, and that will be exactly like we saw on the previous slide. The motion is going to be delayed relative to the motion of the guide roller. And now, if the sensor is very close to the exit roller, the sum of all the delays in the control loop usually increases to a point where the system is no longer stable. We're going to look at a simulation of a steering guide based on the parameters shown here. The pre-entry span is 0.75 meters, entry span 1.5 meters, exit span 0.75 meters, and post-exit span 1.5 meters. The simulation you're about to see is the result of a step change at the pre-entry roller of 1 centimeter in approximately half a second. The animation shows a graph of the lateral position of the web versus distance along the 4 spans in succession. Green vertical bars mark the span boundaries. The yellow-colored bar marks the position of the sensor. The vertical scale is lateral position in millimeters. The horizontal scale is distance along the web in meters. You can see the step coming in on the left, progressing through the other spans gradually. And now it's arriving at its steady state. It's apparent from the animation that things are happening to the web downstream of the sensor. Graph A is a time history of the lateral displacements at the sensor, the exit roller, and the post-exit roller. There are big transient swings immediately after the disturbance, plus persistent errors in the steady state. To help understand what's causing this, let's run the animation again, but change the vertical scale so we can see more detail in the exit and post-exit spans. Notice that the slope changes at the point where the sensor controls position. The guide can control position, but it can't control slope, so the web just seesaws around that point of control. Here's the explanation for what you just saw. The entry span has to bend as the steering guide makes a correction. That requires a lateral force at the downstream end of the span, and that creates stresses which pass over the roller and produce angular deformation at the upstream end of the next span. There are times when there's no way to avoid having the entry and exit spans in the same plane. But it's important to be aware that there's a price to be paid for doing this, because pivoting of the guide roller alters the in-plane angle of the upstream end of the exit span. This produces a steering action that causes a large steady-state guiding error downstream of the sensor, 2 millimeters at the post-exit roller in this example. The next slide shows an animation of this system. It's the same as the steering guide of the last example, except for the angle of wrap. Okay, the step disturbance is coming in from the left. You can see the sensor is just 1/8 of the way down the exit span, and the web's pivoting about that control point. And there we see steady state. These two graphs show the effect of moving the sensor down the exit span. There will be some sacrifice in system stability, but this may be an acceptable trade-off for a significant reduction in error. The seriousness of the loss in stability will depend on the quality of the guiding system. In graph A, it can be seen that putting the sensor halfway down the span reduces the error at the post-exit roller to 1.2 millimeters. Graph B shows that at 80% of the way down the span, instability is evident in the high-frequency oscillations. The next slide shows an animation with the sensor halfway down the span. We see the step coming in at the left. The web's pivoting about the control point halfway down the span, the yellow line, the yellow vertical line. Now we're in steady state. Now I'd like to introduce you to weave regeneration. This is a phenomenon that was first reported and analyzed by Lisa Sievers in a 1987 thesis. Her work was sponsored by Kodak, and apparently someone there had noticed that when a web guide was used to correct a slowly weaving error, it would reappear downstream of the sensor. This is the kind of thing she saw. On the left is a graph of the oscillation input to the system. It's 1 centimeter amplitude at 0.2 of a cycle per second. And at the sensor, the guiding error is 1/10 of a millimeter. But at the exit roller, it's 0.4 of a millimeter. And at the post-exit roller, it's a full millimeter. The problem is similar to the one described for the SRAP steering guide. However, instead of being caused by the direct effect of the guide roller on the exit span, it's caused by changes in the angular orientation of the web at the entry to the guide roller. As the system responds to an oscillating upstream error, the angle between the web and the guide roller axis weaves in and out of a perpendicular relationship as the guide tries to correct it. This angular variation, unseen as it passes through the sensor, is passed through to the downstream end of the exit span, where it alters the entry angle there and causes tracking motion, thus regenerating the lateral error. The variation then passes in the same manner to the subsequent spans. Increasing the accuracy of the guide system won't help because it can't control the slope of the sensor. And the video in the next slide is an animation showing this behavior. Here we see the weaving oscillation of 1 centimeter amplitude entering the pre-entry span on the left. And you see what's happening. The web's pivoting about the sensor guide point and changing the angle downstream. Sievers constructed a lab machine that exhibited this behavior and developed a multi-span mathematical model which accurately reproduced it. An improved version of this model has been used for all the simulations in this paper. It's done using FlexPDE, an FEA software tool for modeling differential equations. Sievers developed two models. One used a simplified beam model, the Euler-Bernoulli beam, which includes only bending stress. The other used Timoshenko beam theory, which includes the effect of shear. Shear is important. Without it, the steady-state error, visible in the step response of the steering guide, would not be seen. Furthermore, the Euler-Bernoulli model underestimates the error amplitude of the oscillating disturbances. For example, the amplitude of the weave error just presented would be 0.7 instead of 1 millimeter. The Timoshenko version was used for this paper. Now we'll discuss the champion of intermediate guides, the displacement guide. It's very similar to the steering guide discussed earlier, except that the rollers are mounted on a frame so that both the entry roller and the guide roller pivot in tandem about the pivot axis in the pre-entry span. This arrangement has a number of advantages. With the displacement guide, there is no downstream regeneration of a step error in the steady state. This is due to the fact that the entry span isn't bent. It's rotated as though it's a rigid body. Overall deformation of the web is minimized. The out-of-plane twisting of the pre-entry and exit spans produces very little stress compared to the in-plane bending of a steering guide. Furthermore, the twisting is symmetrical, so it can't create regeneration issues. Dynamics are simplified because steering is always neutral. There is no over or understeering. And in the steady state, No lateral traction is needed to keep the web in position on the guide roller because of the absence of lateral deformation. In the next slide, you'll see an animation of the displacement guide responding to a step input of 1 centimeter. You see the step input coming in on the left. There is some transient error at the post-exit roller, but that disappears as it achieves steady state. But no guide is perfect. The displacement guide still shows weave regeneration. Response to an oscillating input is very similar to that of a steering guide because the transient response, when the web is not in a perpendicular relationship with the axes of the guide rollers, is similar. In the next slide, a video animation of a weaving web shows this. Here we see the lateral oscillation entering at the pre-entry span on the left. The web is oscillating downstream, and it never has a chance to get to a steady state, so the oscillation downstream persists. I need to mention a few words of caution. All mathematical models are based on approximations and assumptions and should be used with caution. Other than the normal entry law, no account is taken of web behavior on rollers, and there is much we still don't know about this area, particularly lateral microslip. Models are based on the assumption of perfect web traction on rollers at all times, and little research has been done on traction requirements during transient conditions. Siever's tests on the Timoshenko model were successful, but they were limited to weave frequencies of 17 thousandths to 67 thousandths of a hertz, using only one web material. There are some things we're sure of and are well supported by field experience. You won't go wrong using 90 degrees of wrap between the entry and exit spans of a steering guide, with the plane of the guide roller pivoting in the plane of the entry span. There is a reduction in system stability as the sensor is moved down the exit span. Never put it in the post-exit span. There's a steady state offset error when the entry and exit spans are not at 90 degrees. And when precision is critical, a displacement guide is a good choice. A few comments about the future of web guiding. Once a guide system is installed, a customer expects it to operate without attention. And since web dynamics change considerably with variations in materials and line speed, the reigning paradigm for vendors has been to keep the control system simple and use good application techniques to avoid problems. However, new applications such as printed electronics require higher accuracy and are putting pressure on this approach. Powerful embedded computers and better web models make it possible to apply advanced control techniques which automatically adapt to line and web properties without placing additional demands on the customer. Systems like this are currently emerging. They've been reported at iWeb and in the literature and have the potential to make considerable improvements in the capabilities of available systems. Some representative examples are shown here.